Yeah, we'll start. It's only a small summary. Yes, so far what we have seen is that Hadoop kind of introduction, big data and Hadoop introduction, and HDFS. So this HDFS and MapReduce are the core components of Hadoop framework. So far we have seen the HDFS, and probably it's still going to go on for today, and if anything is left, yes, we'll continue that in the next session. So, but these are the two core components of Hadoop: HDFS and MapReduce. HDFS is for storing, and MapReduce is for the processing. So basically, that was the problem with the big data. First thing was storage. Second thing is the processing, and this gives solutions in the form of HDFS and MapReduce. I mean, there are more components down the line, but these are the most important and core components. So in the last session we have seen the differences between a regular file system and Hadoop distributed file system. So what was the problem with that the existing file systems, and why we needed a new file system. So the problems we have seen, a couple of them is that the block size in a regular file system is of 4 kilobyte. Which is way too small, and the block of HDFS is normally by default 64 MB and sometimes 128 megabytes depending on the version we are using. So the problem with this is if it is too small, and say if you are processing say 1 terabyte of data, so that would make up too many of these 4 KB blocks, and each one block is spread across the hard disk at different locations. If it is a really a big block, normally it is stored contiguously. So if the head in the hard disk, when it starts to read, if it is a single contiguous block, it reads faster. So if they are really small blocks and spread across, say a million blocks spread across, so it has to go for multiple seek operations, a million seek operations. That would significantly reduce the performance. So that was the advantage. And we have also seen if the block size is too big, what's the problem? So we are talking about if the block size is big, seek time is less and it's really faster. But what if the block size is really big, so that we can actually fit our file, so whatever we are going to process, into this single block? And this would go against the actual concept of this Hadoop. So the main concept is we're going to divide this job into smaller jobs and process them parallelly. So if it is a really big block, and it is going against the parallel processing. So these are some key features of HDFS. We have covered most of them. It creates multiple replicas of each data block. So it is going to create a data set, say of 1 terabyte. It's going to divide them into multiple blocks, and each block will be replicated 3 times by default. So with this, the data losses would be minimized, and so this MapReduce jobs, and we're gonna come across this when we get to the MapReduce, so don't worry about it. And it also stores the metadata and the blocks, so that it would understand what makes up the whole file. So and also the blocks, we're going to say it probably today. The blocks will be the replicated blocks will be stored on separate So I think Sunil is also here. So the replicated blocks would be stored on a separate nodes. So we're going to also see that again. So that's a small summary, and that we also created. Oh, yes, a small quiz. Let's go through this. Yes. So these are things we have covered. I think it is in a preview mode. Okay, so I was when I was preparing it, it didn't start in the slideshow. Otherwise, this should be starting as a like a questionnaire, but the answer is right there. So, which of the below is not a file system? So yesterday we have seen the other three file systems. ext3, the one we are using, and ext4 is the latest one. So that close. And HDFS is something that we are using. That's taking too long. Let's start with this, our regular one. So, I mean, that's taking a little more time because I've been running virtual machine. In the last 30-40 minutes, it's slowed down. So today we're going to see the architecture. So the architecture, how, I mean, these things are connected, how, I mean, they work. So, I mean, the major components we're going to see in the architecture are the data nodes and name node and their responsibilities, and also how these blocks are spread across these data nodes, and how the name node would actually maintain this metadata. And after that, there are, I mean, a couple more concepts: FS image and edit logs. And after that, we're gonna see, I mean, some problems and solutions, and then we're gonna continue with our last hands-on session with that working with HDFS, and we're gonna see a few more commands. Give me a minute. Uh, Hi, sorry about that. Uh, so yes, we're going to go through this data node and name node. So basically the data nodes are the nodes which are going to store the actual data physically. Yes, this is the agenda for today. Uh, so we're going to see how this Hadoop cluster is and the responsibilities of the name node and data node, and the hardware configuration specific to HDFS, so you get an idea what makes the difference between the data node and the name node. And we're going to also go through FS image file and also edit log file. So probably I could change that. We're going to go through those two new things, and we're going to continue with our hands-on with HDFS from yesterday. So there's two new things, data node and name node. So the data node is the one actually holds the physical data physically. So the data nodes are called kind of dumb terminals. So they don't make any decisions, or they don't do much except actually storing the data in the form of blocks. Because even before the data comes to these nodes, they are divided into blocks, and all they know is what blocks they are holding, and they wouldn't know these blocks, what blocks make up a file, or if there are the replication factor is 3, and where are all the other replicated blocks on the other nodes. They don't know anything except what is in their disk, on their disk. So the blocks are divided and stored across these data nodes, spread across the data nodes. Say if there is a block 1 and block 3, two blocks are stored on this node, and block 2 and block 3 on this node. So what if we could store block 1 here and another block 1 here and another block 1 somewhere else? So the reason is, if the whole concept is that to have a replica if the node goes down. So we can't have, if we have replication factor 3, that means that is the default number, every block is replicated 3 times. If all the 3 are put on one node, right, so we are going against this whole concept, because if the node goes down, 3 blocks are gone, so no replication. So they are spread across the nodes in a way that no two replicated blocks are on the same node. They are always on different nodes. So the data node only knows its blocks, and it doesn't know anything at all. So we need someone to actually oversee these things. So what blocks going where, and what blocks make up what file, and if a node goes down, where are the other replications? So there comes the name node. So this is the total architecture is like master-slave architecture. So this name node is the master here. So it also, apart from this block numbers and their locations, it also hold the file name and the file size, exact block locations, permissions, and created by, and the created on the timestamps, and if it is modified. So it holds everything. So data nodes, they just hold the data, and the name node holds all the metadata, and name node doesn't hold any data. So no data is copied to the name node. So yeah, this is how the data flow is. So initially a file, whatever we are uploading to the HDFS, is divided into blocks depending on the block size, and then they're going to go through the name node and store down all these data nodes. And if its replication factor is 3, every block is replicated 3 times on different nodes, and the name node doesn't hold any data. I mean, no data blocks ever stored on name node. So all the name node stores on disk, on hard disk, is the metadata of files and folders. So only the metadata. So I mean, probably you might not know exact the metadata is just the name, permissions, date, timestamps, everything. So no actual data is stored at all. And the block locations are not stored on hard disk. So every time we switch on the name node, it is going to create a table like this in its RAM. So the block locations are stored in the RAM. The reason is, so if it has to, construct a file using these block locations and their replications, and it is going to perform so many number of operations. But if it has to do that every time by going to the hard disk and coming back, reading and writing to the hard disk, going to take a lot more time, many more times than actually performing the operations in the RAM. So that's the reason why it holds these block locations in the RAM. But whenever we actually turn off a system, the RAM is cleared off. Only the data on hard disk persists. So how it is going to get these block locations? So it is actually from data nodes. So they store the data. Apart from that, they do just one more thing. They're going to send hot signals every 3 seconds. The signals also include that whatever blocks they are holding. So initially when we start, when these data nodes are looking for this name node, they're going to send all their blocks data to the name node, and it is going to construct a table in its RAM of all the block locations and start working on it. And also these data nodes continuously send kind of heartbeat signals every 3 seconds to the name node. So it's the responsibility of the data node again. And so that name node would know actually this node is active or alive. If he doesn't receive that heartbeat signal if more than 3 seconds, it is going to mark it as actually as a dead node. And when another request comes for any block staying on that node, it is going to send that request to another node, data node, where it is holding the replication. So this is to give you an idea of what will be the difference between this name node and data node physically, if it is in a real cluster. So the name node here, what we are looking at is the processing power, the RAM and hard disk. So the process for both of them are same, but it might change in different situations. It might not be the same, but the real difference is in the RAM and hard disk. The reason is the name node doesn't store anything, but it is going to perform all the operations in the cluster. So it needs a bigger RAM, but it doesn't need a bigger hard disk. And the data nodes, other way around, they don't need bigger RAM because they don't perform any operations. But they need a bigger hard disk because all they do is hold the data. So that's where the biggest difference lies between a name node and a data node. Physically, this is physically, just to have an idea how it is in cluster. So the RAM for this name node is 128 gigabyte, and the hard disk is that connected 1 terabyte, that 6 terabyte, and the RAM for this data node is 64 gigabyte, and the disk size is 12 to 24 terabytes. So with that, let's move on. So far it's that the requests are going to come to the name node, and name node knows where the blocks are related to this file, and it is going to construct a file using those blocks or make changes, then uh, respond to the request. So but what if the name node fails? What could happen? So this is the only this is called what? Single point of failure. So if this goes down, whole cluster, whole system goes down. Because the reasons, so there is no one to process any requests because all the DOM terminals, and the data is there, but how to recover the data? I mean, there is no way, because the only person who knows, I mean, what blocks make up to what file is this name node guy. So even if the data is there in the hard disks of these data nodes in the form of blocks and with the replications, 3 replications, we have the data multiplied by 3 times, but there is no way to recover the data because all the metadata is on name node. If this goes down, everything goes down. So let's see, I mean, if this goes down, so these are the things would go wrong. So the metadata goes missing, and there is no read-write operations. For that matter, there are no operations at all. And there is no way that we could know that what blocks make up to what files, and no job can't be run on the cluster. So the whole cluster is down. So this is what they, calling as single point of failure. So what could be the solution? So before we get to the solution, that is another name node. It is called a secondary name node. But having a secondary node is not that straightforward. So this goes down, this kicks in because there is a couple more operations in between, and we'll see what are those and what are the issues with them before getting to the secondary name node. So if the name node goes down, we need a way to actually, start the or get another name node and put this up, the cluster. So for this, what we need is all the metadata. So how to get that metadata? So one way is that the name node maintains FS image. FS image is exactly like the image you got with the softwares, VMware, and an image of CentOS. The CentOS has everything already pre-installed. So it has got the image is exact the image of the total system at that point of time. So you get the image, and then at that point of time, how exactly everything is there, you can get everything back. But there is also little problem, because this FS image can only be maintained on hard disk, because when the system shutdowns, the memory in the RAM is cleared. So we'll have to maintain this in a hard disk. So updating this FS image on the hard disk involves a lot more read-write operations on the hard disk, which would drastically bring down the performance. It is going to slow down the name node, all of the operations on the cluster. But we can't hold that in memory, because when it shuts down, it is gone. So what is another solution? Let's say. So a solution comes in the form of edits log. So edits log is a smaller file. So whenever there is a change for any file, uh, create a new file, update a new file, and anything will be recorded in the edits log first. But this is a small file, so it is not, I mean, creating a little bigger file. So it is a really small file. So it would be a little faster than actually writing to FS file. So this is a small kind of edit log. And then periodically, this edit, I mean, whatever is inserted into edits log will be merged with into FS. So there would be a background process would be running periodically. So uh, every 10 minutes or 30 minutes, it's gonna merge into FS. So it doesn't have to this update a new FS. I mean, almost every second, because there would be something a job would be running through. So this gives, I mean, a solution in the form of edits log. So it is going to hold the few logs, and then periodically when time comes, and it is going to write them into that FS file. Now we can come to the secondary name node. So what does this secondary name node does here in this architecture? So the secondary name node, uh, it is not gonna, I mean, serve any requests. So it is not gonna handle any requests. All the requests still gonna go through name node. But the one thing it is normally does is it is gonna request for this edits log, and it would already be, I mean, having that FS image with it, and because it would be periodically copying it along with this edits log. So it is going to ask for this edits log file from the name node, and once it gets it, I mean, before the name, there is one more operation here. Before the name node sends the edits log to the secondary name node, it is going to actually rename it to edits new and send it over. And the secondary name node, it is going to merge this updates into that FS image and then write it back onto the name node. And the name node would, I mean, rename that edits new to edits and gonna start writing the new requests. And this is gonna happen periodically, say every 1 hour. So every 1 hour, so the secondary name node, what it does is get the edits log and merge the changes with the FS image and write it back to the FS image on the name node. Yeah, so far so good. Now this works. So it's a simple operation, but some of these responsibilities the secondary name node is taking up, I mean, writing and merging this FS image. Because if you go back here, we said, I mean, these things are going to take the processing time, so it is going to slow down the jobs, running jobs. So this name node, basically, it is going to run everything on the cluster. So this is going to be an extra burden on it, and which potentially slow down the performance. So this secondary name node, if it is handling this, writing edit logs into the FS image, this would make this name node a lot faster. So these are some of the name node recovery process, but still we haven't seen what if the name node goes down. Is the secondary name node is going to kick in and start acting as name node? And now still not that straight away, because these are the, I mean, 3 ways we actually, yes, solve the problem when the name node goes down. So one is, if the name node goes down, say there is a the power connection gone to the name node and it shuts down, and copy the edits and logs, the edit log and FS image, and then bring up a new node and copy everything else into it and put it up. So you will have a new node coming in acting as a name node, and then it will technically copy these two files onto the new node, and then it would make it as the name node, and the secondary name node still work as a secondary name node. And the second scenario is you would make the secondary name node as the primary name node. So in these two situations, there are few issues. So making a new node as a primary new node or the secondary node as a primary node is involves a manual intervention. So they're not going to actually kick in straight away. So if it is a shutdown, that probably we could get this this log file and the FS image on secondary name node, and then use another node or use the same secondary name node and put it up as the primary name node, and it is going to start processing the requests, incoming requests. Probably they needs a DNS name change, because we are technically turning this into a primary node. But the small problem is someone is manually doing it, so there is a little gap. So once this went down and then this came up, a new one. So after this went down, there was few updates which are on primary name node, not updated on a secondary name node. This makes sense. So we were talking about the secondary name node gets this edit logs and FS image updated, say every 1 hour. So it has updated around 10 p.m. last night, and then the name node went down around 10:45. So the secondary name node is holding the image is 45 minutes old. So whatever updates happened during these 45 minutes, it hasn't got it. So there is a data loss. So there is periodical updation is every 1 hour. So what happens if the name node goes down in between? Say at 10 there was an update, and 10:45 the name node went down. So all the updates happened in this time span of 45 minutes are not updated on the secondary name node. So even if we get that FS image, we are still missing 45 minutes of data updates. So that's one problem. And the other problem is if the name node went down, the hard disk is okay, then we can still get this files from the hard disk and then use a new name node as a primary name node. But it is going to take some time as manual intervention needed. So this brings down the whole cluster to this period of time. And there is one more approach called high availability, and this is a new setup, and which they are using at the moment. We're gonna go to, yes, we're gonna continue with that hands-on HDFS. So in the next session we're gonna continue with this high availability approach, and once we finish with that we're gonna see a few more comments, and we're gonna move on to MapReduce. So far, did they make sense? Shall we move on to this? Hello?
Yes, Srinivas.
Yes, shall we continue with that HDFS hands-on, whatever we did yesterday?
Yeah, so far you have covered the HDFS architecture, right?
That's correct.
Okay. Okay.
Right.
Yeah.
Okay, all right. So let me see if that a small quiz I created before starting the session. If this comes up, we're gonna. This is like a brushing up from yesterday's session. So I mean, when we come back, so for the next session, I mean that would be on Monday. I think. Hello, it's Ramya.
Yes,
Because of
I'm
the prior commitment, I told you that I won't be
yes, yes.
available this
Yeah.
from tomorrow until
Yeah.
Sunday. So next session would be on Thursday.
Monday, right?
Oh,
Next session
sorry,
would be on Monday.
Monday. Yeah, my bad.
Yeah. Yeah. That is on 19th.
Yes, that would be on 19th. So there we're going to see a bit of HDFS, and if that is finished, we're going to get into MapReduce. So where we're going to spend more time there.
Okay.
So I mean that's loading. This is like a brushing up from what we did yesterday. So we have seen few file systems yesterday. So one of these is not an actual file system. No, not that one, because ext3 we were using, ext4 is the latest one, and HDFS is something we are working on. So that's the right answer. Yes, this is an interesting one. So if you remember, we were talking about block sizes. So when the data set is divided into blocks, so there is a default block size. So in the NTFS, the block size is normally 4 KB. So in the question it is saying that block size is 32 KB. If you are trying to store a file of 5 KB, how much space that would occupy on the hard disk? Will that be 5 or 32? Because that's the minimum block size. So it is going to occupy 32 KB. Regardless of, I mean,
Yes.
if it is even, I mean, less size, it's still going to take up 32 KB because that's the minimum block size that I mentioned. Let's see. Yes, I mean, this one also I mentioned. Uh, so coming to HDFS, the block size is 64 megabyte, but the block size on the underlying, say, Linux operating system is 1 megabyte. So if we are trying to store a file of size 5 megabyte, how much space that file would occupy on an actual hard disk at the physical level?
It should be 5 MB, right?
Yes, correct. Yeah, because that local file system would take the precedence when actually storing on the physical level. So this is only a large scale level on top of the existing file system. So I think this last one. So the concept of HDFS is based on of the below file system. This is one of the first session. So when
Or
dark cutting started,
EXT.
I mean, working on trying to index all the web pages. So we ran out of space, and I was looking for the solution, and the solution came in the form of the Google's paper published. So the Google published a paper with their own file system, which they were working on, and he actually used that technique to build this HDFS, which is GFS, Google's file system, on which the actual Google is running, crawling the web, I mean, all internet web pages and indexing them. So
Hey,
using the same logic, he built this HDFS.
Srinivas,
Yes.
can you go to the question 3?
Yes, let me, no, is that, there's no back button. Shall we come back again? Because this is the last question. We'll go back to 3 after this one. So what is the default replication factor in HDFS? So that would be 3, and we can actually change it. So that is editable, but that's the default one. This one isn't it?
Yeah.
Yeah, okay. Yes, so the HDFS existing operating system, which is normally Linux, would have, its own file system. So when we are talking about the nodes, say 50 nodes across the cluster, and we are using HDFS, which forms like a logical layer on top of it, but in the nodes, we still would be having the Linux operating system. So that, trick in the question is, here it was asking on your hard disk. So at the hard disk level, it is still ext3 or ext4. So, the HDFS is a logical layer on top of it. So at the logical layer level, still we would be losing 63 megabytes. But at the hard disk level, it is 1 MB is perfectly fits into 5 MB. Then it is still 5 MB.
Yes, got it. Yeah, it makes sense.
Let's try this. Okay. So that's opening up. Meanwhile, let me open this command prompt and let's continue with yesterday's.
Hey, Srinivas, since you opened the VMware, right? I installed the VMware.
Yes, yesterday I think I did miss a couple of commands which should have seen at the beginning. One is to check that version of the Hadoop. Okay, this came up. Let me try this. So we call this as, okay, where the actual data is stored, which are the data nodes. So this forms a series of data nodes. So the data nodes would be having their own operating system. So normally that would be some flavor of Linux, which would also be having its own file system, integrated file system, say ext4. And HDFS is a logical layer on top of it. So in the question, he was actually asking, the trick was that he was asking on the hard disk level, physical level. So here the block size, default block size is 64 megabyte. And here it's 1 megabyte. And the logical layer actually, if it is, someone is trying to store 1 megabyte of file. So here actually the minimum block size is 64 megabytes, so 63 megabytes would be wasted. But when it comes to, sorry, said 5 megabyte. It's another 5 megabyte. So 5 megabyte file here. So it's trying to store 5 megabyte file here. So here technically 59 megabytes should be wasted, but the actual data is stored on this data node which is running Linux at the end. And it is having its own file system which takes the precedence while actually writing to the hard disk. And this ext4's block size is 1 megabyte. If you are writing 5, this is going to go into 5 blocks, so nothing is wasted. So that was a little tricky question, but I mean we don't really have to worry about the block sizes, everything on this underlying file system or Linux file system. Does it make sense? So shall we start with few more comments from where we left off yesterday? So one command we missed at the beginning was to check that Hadoop version. So as Ramya asked, I'm gonna share that list of commands, whatever I was typing in yesterday. I'm gonna type them and share through the email by end of today. So this to check that Hadoop version, and this image is running 0.20, and there are two Hadoop versions, 0.x, and here it's going to change. There are a few more, and 1.x, and at the moment we are using this one, and the new updated image it would be having probably 1.x. So this one is to check the Hadoop version, and probably yesterday we have seen it, and in case if you have missed or if you need anything, so all you need to do is help, and you're going to get a list of commands. And then to check the amount of space used or available on HDFS, it is Hadoop FS FNDF HDFS colon and slash. Yes, working. So that's actually displaying in bytes. So the one difference in that we won't be able to see it until and unless we have a real cluster is that say if I do run ls here, so it listed files, and if there is a, say in cluster, I would be having few more nodes connected in network, and if I go to any other one and run the same ls, and there would be a different set of these folders and files, and some of them would be common anyway, but across all the cluster, any nodes, if there are 50 nodes, you go across 50 nodes. If you run this ls on local file system, and you get a different set of these folders, but across 50 nodes, if you go there and run this command, you would get the same list of files. So does it make sense? So this file system would have a global view. So you go to any node and list the files and folders, you see the same ones. But on different nodes, I mean, you run this ls, the local file system, and you see a different set of files and folders every time. So that makes, I mean, here probably you could, here we could see the difference. Say there's a node 1, node 2, node 3, and up to say node 50. So in each node, if we run, there is a local file system ext4. So when I am running actually ls, this command ls is actually run on ext4. This one is ext3, so technically it run on ext3. But this one was running on a top layer HDFS file system. So these two are working one on top of other. So the upper one is, the top one is HDFS, the below one is the local node file system, which is ext3 in our case. So where are we? So checking, yes, checking the available, I mean, space on HDFS. But you can run this from any data, I mean, data node, sorry, any client, and you see the same numbers. So let's go and check the replication factor. Let's see this. So the replication factor, I mean, we don't have any special command to check it. In the list, if you list it, and it is gonna show that replication factor. So let's see, I mean, what kind of files we created yesterday. Let's run ls. Look, fs ls was user training, and we created HDFS one. So there is a test 1 and test 2. So this number 1 and 1 are the replication factor this file is having, are the number of replications this file is having. So are you wondering why this is just one replication? By default it should have been 3 replications. Let's try changing the replication and see what happens. So the command is setrep with a couple of flags. So which one we are going to do? Say test 1. Sorry, it is already there. So it's already there. All I need to do is test 1. But yeah, the changes. So that would be setrep. So that's a replication factor. -r, -w, that's a capital R. And let's see what happens when we try to set replication factor 2. And so where we are mentioning what is the number. So we also need to mention the number we are setting to. Let's do this 4. So at the moment it's only 1. I'm not even trying to set this to 4. Let's see. So if you could read the messages, replication factor 4 is set, and then it is saying waiting for something. Try to come out. No, no, no. It is kind of hanged. There is a very good reason why this has hanged. So I may have to, restart this prompt. Let's go back there. Still there? Yes. So let's run this again. So earlier it was 1, and now it has become 4. So it actually successfully changed it, but why did it hang? So the actual reason is this image, it's a single node cluster what we are using. So when it is changing the replication factor to 4, it has to go through, doing the new replications of 3 more and place them on different nodes. But we unfortunately have only one node. It can't place the replications of a block on the same node. Does it make sense? So the main reason is it's only a single node, and it was trying to find other nodes, but it couldn't. So also, yeah, check. We also going to check the block size. I was talking about the default block size is 64 megabyte, and in some newer versions it's 128 megabyte. Let's check this. So it is FSCK, Hadoop FS. This time it's not FS, directly FSCK, and check the block size of what file. Say we're gonna check for this test2 user training and HDFS1 test2. So there's 2 files. Right. So this has given the actual block size, but this is not actually displaying the default block size. So what's on actual file is just 59 bytes. So this, in browser it is a bit clearer. Let's go and check that in browser. So in HDFS1, the test2. Say it's localhost 50070. So go through the browser file system in the user training and HDFS1. So there is a block size, 64 megabyte. So we can also see the replications. Is 4 and this one is 1. So let's go back and try changing the block size of test2. So the command would be Hadoop FS. This is it's uppercase D.
Srinivas Ramya here.
And where we set the block size is dfs block dot size. In some version, this is block size without a dot. There was a little confusion even for me at the beginning. So to set the block size, we won't be able to do unfortunately on the HDFS. So we may have to copy one file to the HDFS. While doing it, we can actually set the block size. So if you remember when we were merging 2 files, with the get merge, we were having one file in the local folder. No, Ramya, can't hear you. couldn't hear you.
Are you able to hear me now?
We can hear you, Rama.
No. Seriously, I am trying to ask a question, but it seems Srinivas is not able to hear us.
Yes, Ramya, if you want something, you can type that in chat window because I can't hear you. Can you type that in here? So you have set a VMware, but do I have to set further setup? Why replica didn't fall when the system are not available? Don't see Hadoop user file system on my VMware. How can I show for Hadoop? Probably you are missing FS. So did you type Hadoop ls? So it has to be Hadoop fs-ls. So it's a Sunil so typing it, okay. So you can't see that Hadoop file system at all on your VMware. Okay. Okay. So I mean, did you get that kind of right image? So if you could, I mean, share your screen immediately after the session, probably we could see it. We could actually see what's wrong with it, if you did get that right kind of image or not. So, I mean, there would be nothing wrong with the VMware. The problem would be with the image. So if you get that right image and you will have everything set up. Earlier, I mean, before you guys have arrived, I mean, I was talking to Ramya. She was saying that it has got everything set up. We could go through at some point about the installations. I mean, you can do your own installations, but this is more of an administrative job. So Cloudera was giving this image so that we can, I mean, start up straight away. So it has to do something to do with the image. If you might have got gotten the wrong image, I'd probably, I mean, send back on the new image, because we can't even change the image. Probably we may have to go through the whole installation process, which might take another couple of sessions or even more. Hello? Probably we'll do that kind of a session at the end of after we have tried that pig hive and everything, and we go through installing each component. Okay.
Okay.
So, but for now, for you to practice, probably I'll have a look and try to get that right image sent out. Okay.
Okay. I think
So
Peter,
let's finish this off for the moment. Okay.
Peter might be facing the same issue. I'm not sure about.
I didn't try. I didn't install.
So here we are trying to set. Trying to set the block size because the block size is 64 MB at the moment. That's 64 MB. So how to set the block size, and we need the exact number. Let me say if I want to set it as 256 megabyte. So it takes in that kilobytes and bytes. So let me come out of it and run a small calculation. Yes, I want to change that 64 megabyte default block size to 256 megabyte. Oops. Okay, 256 is multiplied by 1024 kilobytes, and this is multiplied by another 1024, and that would give us the bytes. That's a long number, but let me put it there. What was that? 268435. And we are trying to put a file, copy from local or put, which is at home training and Hadoop 1. This should be there. If it isn't there, we may have to, copy a different one. And the destination folder is user training HDFS1. Let's say. Yeah, that worked. And let's come back here and refresh this page. There we go. So we got a new file, test3 from there with a 256 megabyte. That's changing it from here, command prompt. So yes, guys, shall we stop it here? And when we come back, when we catch up again on Monday, so we're going to continue with the whatever is left off in HDFS. If that is finished, we're going to get into MapReduce, and then it is more of a programming part of this Hadoop. And we're going to check that high availability continuation to this, and then if this covers most of the commands used here. I'll see if I missed anything. I'm gonna bring them back by Monday, and probably tomorrow, end of today, I'm gonna send this list of commands, whatever we were typing in yesterday and today, to your emails. And shall we have a look into the image?
Yes. If you can make me the presenter, I can share it.
Before that, can you give me just a minute? 1 minute.
Okay.
Hello? Hello?
Hey,
Yes, Srinivas, are you able to hear us?
Can we get the screen share to have a look at this? Actually, you got the right image and you actually restored it. Hello? It's Ramya.
okay. This is can you all view my screen? Hello, Srinivas?
Yes, I can see Sunil.
Yeah.
Sunil, I think that's running, isn't it? Yes, yes, I can see your screen. Hadoop FSLS is not returning anything because there is nothing there. You may have to run that command mkdir. Hadoop FS training and say Sunil. If you see it in the chat window, that the command would work. mkdir user training and create a folder name. Anything Sunil? Yes, perfect. Now run that ls. Okay, there you go. So basically the home directory is empty when you got it. So now you can, start putting few files from local system to the Hadoop, and I'm gonna anyway send those commands list by end of today, so you can have a play around, so you'll have a better idea. Okay.